Okay, so lecture 7, I think. So we're finishing off shear force and bending moment diagrams, where we've included the UDLs, and that's what we're essentially looking at in this lecture. So last week we did shear force diagrams with concentrated loads and bending moment diagrams. This week I'm going to introduce the UDLs, and where we should be by the end of the week is that problem sheet 7 and 8 should be completed. Last week with the shear force diagrams and the bending moment diagrams. Shear force diagram is straightforward, and bending moment diagram is also straightforward, provided we're looking at concentrated loads. When we introduce UDLs, I agree they are a little bit more tricky. So let's continue our bending shear force and moment analysis. The most important thing is we're looking for is the bending moment graph. Okay. Why this becomes clear, I'll go into the details of it much later, but let's just say for now I'm really curious and interested about where the maximum bending moment is along the beam. So let's recall that the shear force diagram is found by taking the algebraic sum of the vertical forces acting to the left of some position as I'm imagining them going past my beam. I'm going to call this position XX, and I'm going to use a convention that going upwards is positive and going downwards is negative. A concentrated load will cause the plot to shift in a vertical manner, either up or down. The UDL, however, will cause the slope to move with a straight line. The UE convention is that we are going to use that if something, a force is looking positive on my graph, I will be going up, and if the force is going down, I will go in a negative sense. The bending moment value is taken as the algebraic sum of moments acting to the left of the XX position, where the XX position is going to be treated as the pivot. So we're imagining that we've got a moving pivot going across the beam, and we're summing up our moments looking left of us. The bending moment diagram will be a straight line if we are only considering concentrated loads and reactions. However, the bending moment diagram will be a curve in a parabolic profile if we are looking at it going through a UDL. When considering the bending moments to the left of us, taking the XX position to be the pivot, I'm going to treat clockwise moments as positive and anti-clockwise moments as negative. This results in the fact that if I get an M graph that is positive, that part of the beam should be in a state that it wants to be sagging, whereas if we have negative values, then that part of the beam is in a state where it wants to be hogging. A sagging is, let me use my unsuccessful lottery tickets. Sagging is where things are going to be drooping like this, and hogging, I've applied the load and the beam will want to be bending upwards. So last week we looked at this problem, and very easy to draw your shear force diagram. It has the symbol Q. I just look at the forces that I've got. So I've got a 15 kilonewtons here, so I'm going to jump up 15, and then I'm just going to do it like a kind of tachograph where I keep plotting 15, 15, 15 until I come and hit another force. The next force that I hit is this 20, so then I go from the 15 and I'll drop down 20. 15 take away 20 equals -5. Then I just keep going until I hit the 5 at the end, and then wow, I'm back at 0. The fact that I'm at 0 shouldn't surprise me, because what I've done is I've summed up my forces, all my forces in the y direction, by the time I've got to the end of the bar. So when I'm at the end of the bar, I've summed up all the forces, so therefore I expect to be at 0, because I started at 0. Because I had 0 plus the 15. So if you like, we should put in a little line here. We started at 0, we jump up 15, and we go across. Last week I derived the bending moment diagram using the textbook approach of analysing this as a moving pivot. So we've got a moving pivot going across, and the pivot gets to the end. So when I'm looking at the moving pivot, I need to look how far I'm away from the forces I'm interested in. So I'm going to take this pivot to be at position X. So this is going to give me a 15. It's a positive clockwise moment, so plus 15 is a distance X away. So that's my first moment I can see left of me if the pivot's here. And the other force I can see is this downward load force. So it's downward, so it's a minus 20. So it has a 20 value. And what's its distance? Well, to work out its distance, you can simply say, let's take our arbitrary X position and take away its start point. And its start point is going to be at 1 meter. So you open a bracket and you say X, take away 1 wherever the position of that force is, close your bracket. So this then gives you an equation that's valid for this particular region only. And if we move the pivot back here, we can see that we're going to get this equation that's valid in that region. So then you get these kind of plots where you're going to first go up with 15x, and then you're going to go down with 15x minus 20, open bracket x minus 1, which you might want to rework out to be, what was that going to be, minus 5x, and then that will be plus 20. So that line there will be going up to a 20 up to there, but you can see that line is only valid for that particular region. So some of you might have noticed or seen before, actually there's a lot simpler way to find your bending moment diagram than we did following the textbook approach of this moving pivot idea. And if you're doing a simple problem, yes, you could use this, it's not a bad idea to use it. Typically it'll be on a kind of like simple multiple choice type question, not more of a tricky problems that you would have towards the end of your exam paper. So if you had a simple problem, then you might want to be using this approach where all you're doing is looking at the area, and ideally I want to use 2 colors. So we will represent, if I can, I will use blue, I think. Blue as a positive area. Why is it positive? Well, we've got plus 15, and what's its distance? Its distance is 1 meter. So the area that you've got there is 15 times by 1 equals 15. So the other approach you're using is the principle that the M plot is the integral of the Q plot there. So firstly I will have no Q, or I've integrated no Q. Remember, integration is just summing up stuff in little sections. So first I've summed up nothing, and by the time I get to the end of it I should have summed up all that area and get to a value of 15. Now, if I consider the next area, and we'll call this area a red area, so what's its area? Well, its height is -5. We need to keep the minus there. The length of this is going to be 3 meters. So -5 times 3 equals -15. So the next thing to say is, okay, if I'm initially at this point, by the time I get to the end point, I want to take away -15. So you can see what you've got there is 15. Going to take away 15, and we equal 0. So if you had a nice simple problem like that, you probably wouldn't want to use this moving pivot idea, but you probably just want to look at the areas there, and then take one area and whatever. Remember, when you're doing your areas, you're adding on the areas each time, and remember, you need to take into account whether it's a positive area or whether it's a negative area. So here I've started off with 0, I've added on a positive area, then I've got a negative area, so I need to add that on, which means it now drops. And then the start and the end locations, just draw a straight line between those 2 points. So that's an easier way of solving a straightforward problem like that for the bending moment diagram. Now let's talk about the UDLs. So for our shear force diagram, the UDL will create a slope straight line, so that's what we're looking for. And for the bending moment diagram, it will produce a curve, a parabola, as it passes through the UDL. So there are our diagram rules for our UDL to start with. So we'll consider this by considering a real bit of UDL stuck on 2 pivots, and that's what I've got there. So I've got a UDL, it's got 10 newtons per meter. It's 8 meters long, so overall it's going to have 80 newtons, which we can sort of like divide evenly between the 2 reactions. So the 2 reactions are going to be 40 newtons apiece. Okay, could derive that more formally, but that's fair enough. And what's the Q going to be? Well, I know that Q is supposed to be the sum of forces left of me. This has got, first of all, a reaction, which is a positive reaction. It's going upwards. So we've got a positive 40 going upwards left of us. What about the UDL? Well, the UDL in effect is a force that's going downwards, so we know it should be a negative. But you know, how much by? Well, one way to try to analyze this would be say, well, I know what to do if I imagine this to be a concentrated load. So if this was a concentrated load left of my XX line, what force have I got left of me? The force I'm going to have left of me will be dependent on how much distance I've got of the UDL. So I've got -10 times by x, and that will be how much force I've got left of me. So that should work out what my UDL is. So my UDL is going to be, first of all, the 40 coming upwards, and then we're going to take away, we quote the UDL value, so that's going to be our 10, and multiply it by the x, and that's how much we're going to be dropping in terms of the Q. So when we do our Q plot, we start at 40, and then we drop each meter. So let's say this is going to be 8 meters, 4 meters, 2 meters, 1 meter. So each meter I'm going to be dropping by 10 newtons. So that would be 30, 20, 10, 0. Okay, and you can see that's what your Q graph's going to look like. Carry on going down. And then when we get to the bottom, we're going to have -40. Our final reaction will then bring us back up to be a 0 value. So that's what the Q graph will look like. What about the M graph then? Well, this is a bit more tricky, so concentrate. So the M graph, we know, well, let's start off with this force here. That's straightforward. Force 40 going upwards is a distance of x away from that. So the positive moment will be 40 times by x. And what about the bit of UDL that I can see left of me? Well, let's treat this UDL as if it was a concentrated load. So we know that the middle will be some point here. So first thing we've got to do is work out what's the force of the UDL going downwards, and then the second thing we've got to work out is what's the distance from the XX position. So we need to work out the weight of the UDL left of the XX, and we need to work out this distance here from our imaginary pivot to the center of our UDL. So the position to the UDL midpoint left of XX. So the weight bit is straightforward. I did that previously for my shear graph. So that's the UDL value times by x. So that's how much force it's going to be left of us. What about the position to get to the midpoint of get to the midpoint of the UDL from XX? What's that going to be? Well, I know that to get from there to there is going to be x. So can we see what the value is going to be to get back from there back to here? This is the distance we're interested in. What's that distance there? The midpoint is just simply going to be x divided by half. Okay, so that's going to be that distance there that I'm interested in. So let's come back to my M equation. So we've got the 40 times x, take away the UDL value times x, times by the distance to get to it, which will be half x. So our final solution is 40x, take away half UDL x squared. And that's obviously given us a parabola plot. Whoops. And when you come to do these, you're going to, I'll create a video for you, you're going to have to learn how to use the mode button. You press the mode button and then you're going to press table 3. And you're going to have to learn how to code in an equation like this for your more tricky exam questions. So if I substitute in the value of the UDL, which is 10, so half times 10 gives me 5, and that's going to be my final result for this particular beam. That one's easy enough to plot, and you can see what the maximum value is, which turns out to be 80 Newton meters, which will happen as we would expect in the middle of the UDL. And it's a positive value, so that means it's sagging. Again, that's what we expect to get. So the bending moment rule for your diagram rule are going to be that when your beam goes past the UDL, you are expecting to get a curve, which happens to be a parabola. And the way to work this out, although my start position was x equals 0, is basically the UDL value half times by open bracket x, which is the distance from the end point, the leftmost point of the beam, take away the start position of the UDL, close bracket all squared. And this bit here is the magic bit to remember to do to solve how your M equation looks like. So similarly for your Q equation, we're going to have minus UDL value, open bracket, x take away start location of UDL, close bracket. And notice that this bracket bit here becomes half bracket squared basically we're saying x integrating, and we're going to get half x squared. But in our case, we want to put in the start position, integrate that, and then you get x start position squared. So that's what we're doing in effect. So putting in this start bit into the inside the brackets really helps you a lot. Okay, let's consider a more of a challenging problem. So we've got a load, a UDL, 2 reaction points. I've worked out what the reactions are going to be already, so 150. And then I can imagine that, I'm sorry, I'm at 1 meter, that's incorrect. I'm 1 meter away from the start. What's the bending moment going to be? Well, the bending moment I can only see there is going to be 100 times by 1. Now I'm at 2 meters, so if I'm 2 meters away from the left, what can I see left of me? Well, I've got the 100 times 2 now, and then I've got the 90 is coming down, so that's going to be a minus value, so 90 times 1, so it's 1 from there to there. So overall I can then plot that value, and then when I'm in the UDL I can see that what have I got here? So I've got a distance of 2.5 to get back to there, so 100 times 2.5. I've got a distance of 1.5 to get back to the distance there. And what's the distance to go from this location here, this 2.5 position, back to the start of the UDL? Well, that's 2.5, sorry, take away 2, which gives me a half, 0.5, square it. So I could maybe put that half there if you prefer. So we got UDL half 0.5 squared. So that works out to be this number here, 112.5. And what we're going to do to do a plot of this is we're going to learn how to do our table function. But when we're at y location, we've then got 100 times 3 minus 90 times 1. So we've got 3 take away 2, which is start location, so we've got 1 squared, half 1 squared times UDL value, blah de blah de blah. Moving down the UDL, so I'm now at 1.5, and I want to be working out all these values maybe in half steps or even quarter steps, because I want to have a good plot. So I want to produce all these numbers, and I want to produce it at 4. Notice the 4's moved on, this has moved on to a 3, 4 take away 2 has moved on to that value there. I strongly suspect I'm making mistakes here. Okay, no. I don't know whether these numbers at the bottom were actually correct. So move it on to 2.5, we're now at 4.5, 3.5, 2, I'm now at position 4.5, so 4.5 take away 2 gives me 2.5 along from the UDL. And then we're now at the end of the UDL, so we've got 5, 4 and 3. Okay, now let's move just to the right of the UDL, and we should have 5.5, 4.5 and 3.5. Or should we? No, we shouldn't. We're now outside of the UDL. Okay, so that rule of half x take away UDL start position squared only works when we're inside the UDL. When you're outside the UDL, effectively you're looking back and you see this now as one concentrated load pushing down. So when you move right to the UDL, you've now got to treat this UDL as a concentrated load. How much is it creating as a load? Well, 20 times a distance of 3 meters wide, so it's going to create a total of 60 kilonewtons. Then I have to work out, and this is where a lot of people go wrong, I have to work out where the center of my UDL is. Well, it's 3 meters long, so 3 meters divided by 2 equals 1.5, and then we've got 2 plus 1.5, and then that equals 3.5. So the start location, the midpoint location of the UDL relative to this x start equals 0 is going to be 3.5 value. So if I'm at 5.5, I've now got that this is going to create a turning moment of minus 60 times 2. So that's 5.5 take away 3.5. That's where the 2's coming from. Okay. And then if I'm at the end, so I'm now at 6 meters, so we've got 100 times 6 minus 90 times 5, and then we've got 6 take away 3.5 equals 2.5, like that. Okay, you could look at this sort of algebraically. So the bending moment diagram between 0 and 1 is 100 times x. So you could even open your bracket, take away 0, where you're saying that is my start position of that particular force. So you can think of it in those sort of terms. Then when you come to this region here, you can then carry on and do the same sort of rule. So where is the position of that 90 force? It's at x equals 1. So we're going to do x take away 1. I can put it all in a bracket. And then when we go between the UDL, we're going to have 100 times by x, open bracket, x take away 0, close the bracket. Then we're going to have minus 90, because that's coming down, times by x, open bracket, x take away 1, because that's where it's located, close the bracket. And then for the UDL bit, we're going to use the rule of 20 is the UDL. It's going to be a negative, it's coming downwards. And then we're going to use its start location is at x equals 2. So we open bracket, x take away 2, close the bracket, and then we make sure we remember to square it and multiply it by a half. When we're at this region here, we then have to pretend that the UDL goes away and we replace it with a concentrated load at that point there. And so I worked that out to have a total downward force of 60 kilonewtons, and it was located at 3.5 away from the start location there. So the correct equation for the M equation for the region between 5 and 6 is now becomes a linear equation and no longer parabolic. Okay, and then I could plot up the values. Happens to be that at 2.5, I strongly suspect some of my numbers might be wrong now, because I seem to recall that number coming up twice. 2.5 is the maximum M value where it occurs, so that's gives you an M of 112.5. Okay, let's look at a classic example. This is a classic setup, and I'll explain why. We've got an overhanging bit of beam here, force down, and then we've got a UDL section, okay, somewhere between the two reactions. Why this is a classic problem that they like to use in exams, it's nothing to do with the shear graph, so the shear graph looks fairly innocuous. We've got some bit of negative, and a bit of positive. Well, that leads on to something that's quite interesting, and the positive and negative are in the region of this UDL. So what happens not so much here because it's happening on the edge of the UDL, but you can make your UDL a bit heavier or actually a bit lighter, and you can get a crossover somewhere in this region in the UDL. So I'm actually right on the region there, but I can make my point cross somewhere in this region where I'm going to get some sort of parabola like that. And they like using that as a classic kind of exam question, because then you can ask what is the value of m when it equals 0, and you can only solve that accurately if you are using the correct textbook approach, and you find the derivation and so on. So that's why that becomes that's why you need to learn the textbook approach if you want to get those bits of marks in your exam. Okay, and where that m and it changes from a positive, from negative to a positive, or positive negative, where that m crosses and m equals 0, that point is called the point of contraflexure. And it's a structurally interesting point because it's a point where on your beam you're going to get no bending, so you could maybe put a joist or whatever there and not get any bending damage. So that if you're asked to find the point of contraflexure, they're basically asking you where does m equal 0, and normally you would have some kind of function which is basically a kind of quadratic. So you've got m is basically will be forming a kind of quadratic equation, and you're basically setting m to equal 0. So the question is, can you remember how to do quadratics? So you'll be looking for that x equals minus b plus or minus b squared minus 4ac divided by 2a. So you need to be able to use the quadratic find the roots expression to do problems like that. And that's it for that lecture.